Hello and welcome to another episode of the ALEPH Zero Podcast. One of the fundamental elements ensuring the privacy on ALEPH Zero blockchain is the use of Zeroknowledge proofs, or ZKPs as we know them. We'll be meeting today with Damian Straszak, one of the developers building ALEPH Zero, who will guide us through this solution and how it fits into realizing ALEPH Zero's mission of creating new standards for Web3. Hey Damian, let's start with the customary introduction. Please let our listeners know who you are, your background, your experience, and anything else that you find interesting to share.
Hi, it's awesome to be here. So my background is in computer science and mathematics. I did a Ph.D. at EPFL Switzerland on the topics on discrete and continuous optimization. Well, and one interesting thing that I can say besides that is that I used to be an active participant in a sport programming event. And yes, this is a thing. So I just wanted to advertise a little bit because I find it interesting. So these are competitions for either individuals or teams where you write computer programs and you have a per-specified time, you have some tasks, and yeah, this is a cool thing to do, a really nice activity. So if you're a programmer, you're learning programming, I highly encourage to maybe participate in some of these contests.
Where you can find those? What should you enter into Google to
Yeah,
find?
that's a great question. So I would just say you can Google competitive programming or sport programming, and you will find like a dozen of different platforms, including Codeforces, Topcoder, AdCoder, like many of those. And they host competitions probably every week or so. And yeah, you can learn a lot by participating in this kind of contests.
Did you have some successes there?
Well, I mean, yeah, there is a international contest called ICPC, and this is a competition for teams, actually from academic students. So the teams of 3 represent all kinds of schools around the world. And once per year, there is this ICPC finals where roughly 100 teams from all around the world gather, and yeah, they have this last final competition. During my student times, I used to participate in this contest, and I managed to qualify to the Sword Finals, which is, I think, a really nice thing to do as a student, because it is very satisfying. It keeps you motivated to like work on your programming skills, and it's also really fun. So yeah, this is something I can surely recommend to like every student, or not even student. Like this, there are contests like for everyone. Like you can just be a beginner. You have just written your first program, a hello world, and for sure you will find a competition that will be suitable for your level. So yeah, highly recommended for sure.
Right, so that's probably why you are one of the key figures in ALEPH Zero development, I'd say.
Maybe not really key figures, but yeah, I've been doing both research, development, many kinds of things, many kinds of projects already for 5 years in ALEPH Zero, so almost from the very beginning. And well, yeah, I like it here. I like the atmosphere, the team. So we are doing great things. Both research-wise and in development. So yeah, I plan to stay here as long as I can.
Yeah, and you do both research and development, right?
Yeah, that's correct. Like whatever is needed the most at a given point of time, I try to contribute. So that's currently I mostly work on a research project around zero knowledge proofs. I do a little bit of development, but I would say, mostly researching things for our Liminal project, which is about zero-knowledge proofs.
Yeah, so let's dive into that. What are exactly the zero-knowledge proofs?
So let me start from the very beginning. So we need to go back to 1985, actually, where a very fundamental paper came out by Goldwasser, Micali, and Rakov, which introduced this notion of a zero-knowledge proof. And I will be a little bit formal now and try to explain it in mathematical terms, but don't get scared. I will then try to give you an example. So what is a zero-knowledge proof? There are two parties in a zero-knowledge proof, and they have a conversation. So there is a prover and there is a verifier. The prover holds some private data, a secret that it doesn't want to leak. And the verifier, he wants to learn something about the secret, some property of the secret, without learning the content of the secret. So in other words, it wants to validate integrity of the secret, hold some useful property, but the point is to not give him the secret. That would be just obvious, but do it in a different way. Okay, so then a zero-knowledge proof is really something what we call a protocol. It's a way to interact between these two parties so that we reach this goal, right? That the prover convinces the verifier that the data it holds has some specific property. And that's like the mathematical definition of a zero-knowledge proof. And yes, I know this might not be very intuitive, and indeed it sounds a little bit cryptic. So let me now give you this example that you all know actually and use every day. And these are digital signatures. Okay, so whether you have interacted with a blockchain or you are just doing some like everyday web activity, you use digital signatures because they are everywhere. And what these digital signatures really are is a way for the prover, and in this case the prover holds the private key, so some kind of secret data, to generate a signature so that everyone here is a verifier, is convinced that the prover indeed holds this private key. Okay, so this is a way for the prover to prove to everyone else that he is the holder of this private data, but the important thing here is that the prover is not showing everyone its private key, right? So if I sign a transaction on a blockchain, on ALEPH Zero or any other chain, I don't show you all my seed phrase, right? The seed phrase is the private key, and the private key is my secret data they want to keep, and I keep proving to you that I know it, right? I am the only holder of this secret, but I am not revealing it. And that's the point of zero-knowledge proofs. Okay? So this is a very simple example, and it is maybe not very illustrative, but yeah, it is an example that you see every day. So I think it still makes sense to use it to illustrate this concept. And I think another important thing here to say is that, as I mentioned, this concept of zero-knowledge proofs is from the 80s. So it's very old. And what happened in the last decade or so is a lot of progress on zero-knowledge proofs. And in fact, there is a concept which was introduced in the last decade, a snark. And while it is not the same thing really as a zero-knowledge proof, you can think of it as some kind of a practical realization of this zero-knowledge proof concept that we are kind of missing before, and that's why we didn't really see any applications. Now in the last decade, we kind of see a lot because of this progress and because the kind of research that happened over the last decade.
All right, so you mentioned Snarks or ZK Snarks as usual. You usually find them when you type that into Google. So how exactly are they different from zero-knowledge proofs? What's the relationship between them?
Right, yeah, that's a great question. And I would say that in the blockchain industry, these two names are often treated as synonyms. So ZKPs and Snarks or ZK Snarks, like you often hear these terms to be used interchangeably, which is kind of okay on the conceptual level because they are very similar, and for regular users it's really no difference. But mathematically, indeed, they are kind of fundamentally different, as it is usually the case. So let me now give you the mathematical definition and try to explain the differences so that it's clear what we are talking about. So Snarks, right? So the acronym here is Succinct Non-Interactive Argument of Knowledge. And let me go over the different terms here and try to explain. So I will start with non-interactive because that's an important one. And what it says is that previously when we defined zero-knowledge proofs, I mentioned that there is a conversation between the verifier and the prover, right? So they exchange some messages, they talk to each other. And in the example I mentioned of digital signatures, this conversation was very short, right? Because there was this prover who just generated the signature and sent it to the verifier. Then the verifier validates the signature and it's done, right? So it's simply just a single round of interaction. And this is what we call non-interactive proofs, okay? So there is just one message from the prover to the verifier and it's done. In general, it can be many rounds, at least that's what the general definition allows. Okay, so we want non-interactive because this is something very useful for blockchains. So this was the N in Snarks, non-interactive. Then let's talk about argument of knowledge. Okay, so this is analog of proof of knowledge, really. So we need to understand what's the difference between an argument and a proof. And this is actually quite technical. So the way we formalize security for this kind of cryptographic primitives is we talk about an adversary and its power. So in case of proofs are secure as long as, proofs are essentially secure no matter what. No matter what the adversary can do, no matter what's its computational power, the proofs are constructed in such a way that it really doesn't matter what the verifier does, right? And that's a very strong definition of security, but it also then brings some issues. And in fact, zero-knowledge proofs cannot really be made efficient because of this very strict definition. Arguments, on the other hand, have a slightly relaxed but practical definition of security. So it is said that arguments are secure as long as the adversary is not very powerful computationally. Okay, so this is normally how cryptography works. We have something called cryptographic assumptions, which say that some specific problems are hard to solve. And as long as there is no adversary which has a very powerful computer, more powerful than all computers in the world combined and working for 24/7 over years of time, then there is no way to break a particular protocol. And this is what we are aiming for in Snarks, because they are arguments and not proofs. Okay, but this is from the practical perspective, it doesn't matter. From the theoretical perspective, this is fundamentally different, but still arguments are what we want here. And the last property of Snarks is succinctness, so the S in Snarks. And this is actually a very interesting and important one, because it says that no matter how large the secret data of the prover is, the proof showing to the verifier that the data satisfies some particular property that we are interested in is small. And by small, I mean really constant size, let's say 200 bytes or so. Okay, so this is asynchronous, meaning the proof that the prover sends to the verifier is small and does not depend on the size of the secret data that we start with.
I know what everyone would ask you now, and that would be, what about quantum computers?
Great. That's a good question. So what we currently know is that certain cryptographic primitives, such as signatures, might be susceptible to quantum attacks. So in particular, if it was the case that someone built a quantum computer, which we don't know will happen or when, then some digital signatures such as ECDSA or Schnorr or many others would become susceptible to quantum attacks, essentially. So you could essentially break them and pretend that you have the private key even though you don't, right? So this is not very good. But it's kind of orthogonal to what I just said. So you can actually consider arguments both in like a classical way and in a quantum way, essentially. So these are just different ways to define security. If you want to define security like in a more strict way, like you want to be secure against quantum computers, then of course it will be harder to create such protocols. Yeah, if you want to be more classical and just say, yeah, this is our classical definition of security that does not care about quantum computers, then that's a different definition, but it's still fine and it's used pretty much everywhere. So yeah, there is always a certain trade-off. Like the more security you want, the harder it is to create protocols, and they will be typically less efficient in some way. Maybe they will have larger proofs, or yeah, there are many different parameters here that will change with the type of security assumptions we make. But currently, I think state of the art is we are not afraid of quantum computers. And I think most of the crypto systems in the world are susceptible to quantum attacks. But yeah, I guess that's the consensus, that quantum computers are still far away. And yeah, it's relatively safe to still use the kind of old good crypto systems based on elliptic curves and stuff, because that's what matters for quantum computers.
And basically, to like theoretically prevent quantum attacks, you could just turn up the difficulty to a level that is also complex to a quantum computer, right?
Yeah, that's correct, actually. So all these attacks, these quantum attacks, also have some complexity. So let's say if we have, 100 bits of security, then, the attack will take maybe 1 day, depending on how powerful the quantum computer is. But then, of course, if you scale the number of bits, the security level, then the attack will also take longer, even if it's possible. So essentially, yeah, that's a valid point. Even if there was a quantum computer, then maybe we could increase the difficulty level, the security level to such an extent that even quantum attacks would become kind of useless. But well, that's in
the future.
Yeah,
probably a long one.
Yeah.
All right, so back to ZK stuff. What are the applications of ZK and ZK Snarks?
I would say there are two categories of applications that this technology brings. And the first category is all applications related to privacy, because, as I mentioned, zero-knowledge proofs are about keeping some data private. And what it allows is essentially bringing more privacy to blockchains, for instance. So as you know, even though blockchain transactions are kind of anonymous in the sense that there are these accounts and it's not really clear who holds which account, there is no name associated to the accounts. But in reality, it's kind of easy to track the accounts because all the data on a blockchain is public. So it is actually quite easy to associate even real names to blockchain accounts, and hence blockchains are currently understood to be not very private indeed. And with this technology, we can actually improve the situation. We can make interactions with the blockchain more private. And that's one broad category of applications that zero knowledge proofs, zero knowledge Snarks allow us to do. The second category is related to efficiency, to scaling. So as I mentioned, the S in Snarks relates to succinctness. And this is a very important thing that this technology brings to the table, because you can now maybe prove that some large computation happened and yielded some particular result without executing the computation yourself. Okay, so consider a case where there is a block in the blockchain and there is a lot of transaction inside, and there is a validator who not only executes these transactions, but they also compute a proof, a snark, that the set of transaction yielded a particular result. Okay, so the state of the blockchain started in some state, right? And then via this set of transaction changed another. Okay, and then the validator can also create such a proof of what this change was. And note that now, since snarks are succinct, they have really small size, we can now take this snark, this is just 200 bytes of data, and we can verify it very quickly. And we don't need to make this computation again, right? So this is like immense applications to scaling. Essentially what this allows to do is to compress any long computation into a very small one. Okay, instead of processing a block, which could be very large, we are just processing the proof. And yeah, this has already found lots of applications, especially in ZK rollups, where essentially you can build an Ethereum clone over Ethereum and make it run much faster, because everyone now needs to only verify the proofs instead of executing all the transactions. So this is a very powerful thing.
And as you mentioned, the ZK rollups, and of course, some people would say that ZK equals privacy. So does it mean that there is a built-in privacy in ZK rollups?
Right. I am glad that you asked it, because yeah, this is a common misconception. And in fact, the name ZK rollup is a little bit inaccurate. So ZK means zero knowledge, which kind of suggests there is some privacy. But in fact, this ZK in rollups comes from ZK Snarks. So that's the origin of the name. But the bad thing about the name is that actually ZK rollups do not use ZK Snarks. That might be a little bit confusing, and well, no surprise. But rollups, ZK rollups use Snarks without the zero knowledge property. So what this really means, and because we talked about Snarks as really a variant of zero knowledge proofs. So in fact, Snarks without the ZK, and they are useful by themselves because of this succinctness. Okay, so they are just small proofs of computation. And even though the data does not stay private, this is still useful because of this compression of computation. Right? This is something I talked about a second before, that thanks to Snarks, you can compress, execute the block, generate the proof, and then let everyone just verify the proof instead of executing it again. But what's important here is that we don't really care about zero knowledge here. And in fact, it doesn't even make sense, because even if we use zero knowledge Snarks instead of just Snarks for ZK rollups, then there is no privacy gain, in fact, in this construction. So what all ZK rollups use, they use Snarks. Snarks don't have privacy. They have succinctness, and this is what we care about. So yeah, long story short, ZK rollups use Snarks. Snarks are not ZK Snarks, hence they don't have privacy.
Okay, and from my understanding, the ZKP family is quite wide. There are ZK Starks, ZK Snarks, Sonic, Merlin, and Plonk. So how do these systems differ from each other? And as a user, should you care actually?
Yes, there are many such systems. And I would say the situation here is pretty similar to the situation with digital signatures. There are many digital signature systems. There is ECDSA, there is Schnorr, there is BLS, there are signatures that are quantum secure, and many different schemes. And well, there are trade-offs between them. Maybe security trade-offs, maybe generation of the signature is a little bit faster for some of them, but fundamentally they're not different. And it's the same for Snarks. Essentially, for a user, which Snark a particular protocol is using doesn't really matter because the differences between them are quite technical. So most of all, the differences are regarding cryptographic assumption on the security, and there are differences related to efficiency trade-offs. So things like proof size, or how much work is the prover doing, how much work is the verifier doing. These are all important aspects, but they don't really affect the user, I would say. But if you're interested in learning more about all these proof systems, I highly recommend taking a look at these resources. One resource is the ZKP MOOC. You can find it on YouTube. It's a series of lectures given by the best domain experts who explain many of these systems and dive deep into the technical details. So yeah, it's a really great resource to learn about Snarks. And the second resource I highly recommend is episode 274 of the ZK podcast, in which Ariel Gabison talks about the ZK trilogy. So it's kind of about the history of the developments in the ZKP technology on Snarks. And it's also a very interesting podcast, so highly recommend it.
All right, we'll link those in the description. So how does ALEPH Zero implement ZK Snarks into its architecture? We know that's Liminal, but what happens behind the scenes?
Right. So yeah, Liminal is at the heart of ALEPH Zero, and it's essentially a privacy engine. Okay, so using Liminal, we want to make many things private on ALEPH Zero. So in essence, currently, when you interact with the blockchain, all your transactions from your account are public, right? And everyone can see that you did this sequence of actions, right? So you send the transfer, then you made a swap, then you staked some tokens, but all transactions that you made are then clearly linked to each other, right? So it's clear that it's you that made all these transactions. And essentially, by looking at the blockchain, anyone can see the full log of what you did. Okay, it's a bad thing because ideally we would like things to be private and not so easy to see, right? And that's what we want to achieve here. So Liminal is a technology that allows you to get some privacy. So essentially, your actions on the chain will be still visible. So this is something that is often misunderstood. ZKPs will not hide everything. It's still clear that something is happening on chain. Someone is making a transaction, and often it's clear which transaction it is. But what is not possible to see is who is making this transaction and maybe the details of the transaction, right? And in particular, it's not possible to link different transactions of the same user. So previously, without privacy, you could see that this user did A, B, C, D, and so on transactions. Now what you see is that there is like a bunch of transactions. Every transaction was performed by someone, but it's not clear which transaction was made by whom. And yeah, it's also often possible to just hide the details of the transactions, like how much was transferred and so on. So this is something that the Liminal allows you to do. And our goal is to make Liminal integrate easy with the DeFi ecosystem. So in particular, we want privacy for interaction with DEXs, with lending protocols, with staking, with all kinds of activities that you would like to do on the blockchain, but we want to keep them private, right? So that's the goal of Liminal. Okay, so you could ask, but what's inside Liminal then? It's the privacy engine, but how is it built? And well, of course, it uses zero-knowledge proofs. In fact, it uses Snark technology called Plonk. So the first stage of Liminal will be based solely on zero-knowledge proofs. But there is a challenge here, actually. So what I explained before is that zero-knowledge proofs allow you to hide a secret, right? And while the secret is kept by one party only, by the user, everything is kind of simple because the user is creating the proofs. He is showing that everything is computed correctly. So there is always this one party which can certify that the computation was done correctly because this party knows all the secret data. And of course, there are many accounts, but each particular account has one owner who holds the data and can create proofs about it. But this becomes complicated if there is a secret that nobody should know. Maybe this will be the state of a smart contract, maybe a DEX, maybe something that nobody should know until some moment of time. Okay, for this kind of applications, what we plan to do is use multi-party computation because this is something that can allow us to overcome these difficulties, solve problems which require secrets that are shared between many users or secrets that are global and no user should know about. So this will be Liminal, a system which is a combination of zero-knowledge proofs or zero-knowledge snarks and multi-party computation.
And Liminal with only ZK, that would also support smart contracts?
In a sense, yes. You can still integrate contracts with Liminal. So some amount of privacy can be achieved using just ZK snarks. But this will be kind of limited. The answer is yes, you can do great things just using zero-knowledge proofs. But multi-party computation just brings it to another level. You can do virtually everything. Of course, there are some trade-offs, like multi-party computation is kind of expensive in the sense that it requires communication. So it might introduce some latency, but essentially it has no limits as to what you can do with it, which is great. But I think what we want to achieve is have a system which has both, because with Snarks, you can kind of do some things good and efficiently, and with multi-party computation, you can do everything. But yeah, there are this kind of limitations as to efficiency. So combining both, we think, is the best approach.
Okay, so essentially what we are doing with Liminal is finding a balance for privacy framework between speed and probably its the possibilities that it offers, right?
Yes, what you're saying is right. So on the one hand, we have Snarks, which is a technology that is kind of efficient. Yes, the proving time and verification time, proof size are important consideration when designing new proof systems, and they are being refined and improved all the time. But this is something that with time we will essentially get really good at, and I don't think it's an obstacle for this kind of privacy technologies. So we can think of Snarks as really efficient, but currently there is no way to build a system which holds some global secrets shared between many users using just Snarks. So Snarks are good for systems where the state is divided into multiple accounts, and each account holds its own data, and there are no secrets which are kind of shared or which are global to all the users. So one particular example where such a state would be useful is in a DEX, right? Because in a DEX, there are interactions which happen between a couple of users. So either peer-to-peer, like one user is selling, one is buying, or there are these AMM DEXs where you essentially sell to the contract, but there is this state of the contract, which essentially keeps track of the price, right? And if you want to make things private, we need to make the state private, right? And this is something which is not really possible using just Snarks. And that's why we also want to use multi-party computation. Because using multi-party computation, you can have a secret on a blockchain which is not known to anyone. Essentially, you can just toss a coin and keep it hidden for as long as we wish, or we can make some computation on private data. Like, this is something you cannot really do with Snarks. So multi-party computation is a technology that can give us more power, but of course this power is not for free. And multi-party computation protocols require interactions between many parties, and these interactions essentially take time, right? So these parties need to talk to each other, they need to do some computations on the secrets that are shared between them, and well, this introduced some kind of latency in the system. So it's not possible to just send a transaction and now let the committee do some computation like at the very moment and have the results ready right away. It's not possible. There will be some delay. And this delay, of course, is bad. So essentially, the way to proceed is design the system in such a way that as much part of the system will be using zero-knowledge proofs to be efficient, to be user-friendly, to have no latency at all. But then there will be this very little piece, maybe, that requires some more power, right? And that requires to have this private global state. So in MPC, we essentially have this downside that there might be some latency that we need to pay with to complete some computation. Of course, this is something we're actively working on. Maybe this can be reduced, maybe this can be get rid of. It's just something that we need to be careful about when designing these privacy solutions.
All right, and the last one would be to those that haven't interacted with any ZKPs so far. So what are the steps, and as a user, what should you do or what you can do with ZKPs? Especially I'm thinking about, what about the proofs? How do you handle that?
Right, that's a great question. And everyone who has ever tried using a privacy chain has most likely noticed that the user experience is quite different. So you typically need to use a specific wallet to interact with such chains. And well, this can be a little bit cumbersome for many users because, well, they just want to use their favorite wallet and not change wallets in case they want to interact with a privacy protocol or privacy chain. So clearly there are some issues in user experience currently. So another problem is that, well, normally the experience with sending transfers or sending any kind of transactions to the chain is that, well, you click the send button, you just wait for the transaction to appear in the blockchain and you can see its results right away. Well, the situation with privacy technologies, with chains that use Snarks is a little bit different because here the user is often creating the proof, right? So within the transaction, there is a proof that certifies the transaction is correct according to some private data that the user holds. And creating this proof can be sometimes expensive. And well, this is something that can be optimized. And I think over the years, as it happened already, we will be seeing faster and faster Snark systems, faster provers, and will eventually converge to a design which is just fast and does not force the user to freeze the browser for a couple of seconds just to send a transaction, because that's how it is currently. So I think, this is what we need here, is another 1 or 2, 3 or more breakthroughs in the ZK Snark technology, which is something we can expect because there is a lot of brainpower put into research on ZK Snarks, and we are seeing steady progress all the time. And there are aspects about user experience related to the secret data that the wallet needs to keep on top of the usual seed phrase that you normally input to the wallet. So the point is that whenever you interact with such a blockchain and use a privacy system, normally new secrets, new private data is being generated. And the wallet needs to keep the data, which is kind of problematic for the user because, you cannot just remember your seed phrase, and because the wallet also keeps some other data that you should kind of remember. So you should make a copy of it, or you should store it on the cloud. But then when storing on the cloud, then it kind of might affect the security and things like that. So there is a challenge there. And certainly we are putting a lot of work into that to make it as smooth as possible for the user. And I also expect a lot of progress in this direction. And ideally you want a product for which the user experience is essentially the same as for non-privacy products. It's as smooth and as good experience as you would use a really fast chain, but without the privacy features.
Yeah, and I think it's worth underlining that for ALEPH Zero, it will be only a thing for interacting through Liminal, right? So ALEPH Zero itself is public and it works just as smooth as it can be. Only the ZK part is the challenging part, but I know we are working hard on solving that. All right, so thank you for that. I think everyone will walk away from today's episode more educated on ZKPs and also with more insight into how we approach the privacy aspects. So thank you for joining us, and I hope we meet on the show again. So see you soon.